In this lecture, we'll introduce an important electrical property, capacitance. In particular, capacitance will be used to characterize electrical circuit elements known as capacitors, which play important roles in many electrical circuits. To start, let's recall that in earlier lectures, we discussed the electric field near a plate of area capital A and charge capital Q. Let's remember that if we're near the plate and not too close to the plate's edges, the electric field is constant and perpendicular to the plate. Now let's build on this example by considering a special case of two parallel plates, each with the same area, capital A, near one another, where one plate has a charge of plus capital Q and the other plate has a charge of minus capital Q. We can find the electric field at most any point in between the plates. We just apply what we know from our result for the single plate twice. Once for the plate with plus Q charge and the other for the plate with the charge minus Q. Both electric fields are perpendicular to the plates and both contributions point in the same direction, and each of the fields have the same magnitude and are constant everywhere between the plates, as long as we are not too close to the edges of the plates. The total electric field between the plates is then just the sum of the E fields of both plates, and that's just twice the magnitude of the E field of a single plate. Now this arrangement is called a parallel plate capacitor, and we just rewrite the E field for the capacitor as shown using the subscript C for capacitor. If we have information about the separation distance S between the plates, we can compute delta VC, the potential difference across the capacitor. Since the field is constant between the plates, delta VC is just minus the scalar product of vector EC with delta R, the displacement vector. Here we're going to compute delta VC starting from the negative plate and moving all the way across to the positive plate. In this case, delta VC works out to just be the magnitude of E sub C times the separation S. And by substituting in our expression for E sub C, we end up with this result. We now can define the property of capacitance, capital C. This is the ratio of the magnitude of the charge on one of the plates of the capacitor divided by the magnitude of the potential difference across the capacitor. The SI units for capacitance are coulombs per volt. This combination of units is called a farad. Now physically, we can think of a capacitor as a charge storage device. The capacitance C tells us how much charge we can store for each unit of potential difference. To say this in SI unit language, the larger the capacitance, the more coulombs of charge we can store for every volt of potential difference. We can work out the capacitance for a parallel plate capacitor, and it's this, which just depends on the geometry with an overall constant epsilon naught. That's it for this lecture. In our next lecture, we'll discuss how a capacitor works in a circuit that also contains a resistor.